Okay, so today we're going to be talking about uh, calculus and how position, velocity, and acceleration relate. Okay, so most likely when you see in calculus um, x of t or s of t, this is your position. Okay, they're talking about distance. Okay, v of t is your velocity, and a of t is acceleration. Okay, now the AP test will usually use like x of t or p of t. A lot of physics will use s of t, and a lot of students get confused with s of t as speed, but the s actually comes from the Latin spatium, meaning space, so it's position in space. Okay, so here's how it works. So we start with position. When we talk about velocity, velocity is the change in position over the change in time. So velocity is the slope, okay? Now if it were average velocity, it would be change in position over change in time, but when we're talking about instantaneous velocity, velocity is the derivative of position. So if you take the derivative of position, s prime of t or x prime of t, you get the velocity equation, okay? Acceleration, when we talk about average acceleration is the change in velocity over the change in time, which means acceleration is the slope of velocity. But in calculus, we talk about its instantaneous acceleration. So acceleration is the derivative of velocity, which also makes it the second derivative of position. Okay. Now there is another one. So if you take the derivative of acceleration, you get what's called the jerk, and that would be j of t, which is the derivative of acceleration. But we don't use that one as much. But that's like when you have a really rapid acceleration, how it actually kind of, think about it, how it jerks your head back. Or if you stop real quick, it jerks you forward. That's that instantaneous uh, jerk from acceleration. Okay? All right, so one of the most confused things that we deal with when we talk about rates of change and uh, velocity and acceleration is this average rate of change versus instantaneous rate of change. Okay, I see my kids do it all the time. So when we talk about average rate of change, so for instance, what is the average acceleration after the first 3 seconds? As soon as you hear average, so when we're talking about, say, average rate of change is slope, the slope equation, change in y over change in x, or y2 minus y1 over x2 minus x1. This is the average rate of change between 2 points. Okay, you can't find the average of something if there's just one of it. Okay, that doesn't even make sense. So when you see average rate of change, you know that you're dealing with a rate of change between 2 points. Okay, so in this case, we're talking about average acceleration. So average acceleration, so a of t, the average acceleration, is v2 minus v1 over t2 minus t1. Okay, so that's what we use for average acceleration, which means we need the velocity equation. So the first thing I need to do is I need to take the derivative of position to get my velocity equation. So s prime of t, which equals my velocity, take the derivative of this, you get negative 3t squared. Okay. Now we need our v1 and our v2. Well, we're finding within the first 3 seconds, right? After the first 3 seconds. So my initial point is at 0, and my second point is at 3 seconds. So I need to find v at 0 and the velocity at 3. So v at 0 is easy, that's 16. And then, oh, I plugged it in position. So v of 0 is 0. V of 3, so we plug in 3. 3 squared is 9. 9 times negative 3 is negative 27. So now we plug in to our average acceleration equation. So v2 is negative 27 minus 0 over 3 minus 0. So you get negative 27 over 3, or negative 9. Negative 9 is my average acceleration from 0 to 3 seconds. Okay? Now, that's if it's asking for an average rate of change, average acceleration. What if it's an instantaneous rate of change? Instantaneous rate of change means at one point. Okay? So I want to know, I don't want to know the average acceleration from 0 to 3 seconds. I want to know what is the acceleration at 3 seconds, which means I need the acceleration equation, which means starting with position, I have to find acceleration. So we have to take the derivative of this twice. So first one, s prime of t, which is my v of t. We already know that. We did it just a second ago. It's negative 3t squared. But now we take the derivative again, which is the derivative of velocity, which is my acceleration equation. And when you take the derivative of this again, you're going to get negative 6t. And I want to know what is the acceleration at 3 seconds. So we plug in 3. So negative 6 times 3, which is negative 18. That is my acceleration at 3 seconds. Okay, so do you see the difference? The difference is if I'm asked for an instantaneous or at one point, that's when I'm just finding the derivative and plugging it in. Now, if I'm asked to find an average, I need it between 2 points. Okay, which means I'm just using the slope equation. Now, let's put all of this together with what we've been working on. Okay, so how far a car has traveled after 5 seconds when the current acceleration is 4 meters per second squared with a position of s2 equals 138 and a velocity at 2 being 68. Okay, so we need to know how far the car, or what its distance is at 5 seconds, but I don't have the distance equation, do I? No. The only thing I know is that when the time is 2, my distance or my position is 138. And I also know that at my velocity at 2 seconds is 68. And the current acceleration for the car, the function that gives its acceleration, is 4 meters per second squared. This is a common problem, but since I know my relationship, think of it this way. A of t, we just said that, wait a minute, A of t is v prime of t, correct? So this equation that we have for acceleration, this 4, came from the derivative of velocity. Well, what did the velocity equation have to be to get that derivative? Well, that means that v of t had to be 4t, because the derivative of 4t is 4. But there could also be some kind of constant, so I'm going to put a c there. Just like we do in the quadratic equation, it's a squared plus ax squared plus bx plus c. That c at the end is that constant. So we use the letter c to represent a constant, or sometimes the letter k. Okay, so this is technically my velocity equation. Because if I take the derivative of 4t plus c, I get the acceleration of 4. But the problem is that I don't know what c is. Well, can we find c? Absolutely. They gave us this right here for a reason. Okay, you're going to find out very quickly that in a calculus problem, there is no extra information. Okay, if they give you a number or they give you kind of some kind of information, there's a reason for it. Okay, when you were in your other classes in mathematics, they might actually throw in what they call distractor information, or information that you're not going to use. But by the time you get to calculus, you've gotten to this point where the questions are already difficult enough. They don't have to throw anything in there to distract you. Okay, so all of this information is important. And the reason that that's important is because that is giving me what we call it like an initial condition. It gives me a value that if I plug in 2 for t, this better be equal to 68. It's kind of like what we did back in Algebra 1 when we were trying to find the y-intercept, and we'd plug in a point into x and y and solve for the b at the end. That's what we're going to do here. We're going to say, well, if I plug in 2, I should get 68. So 68 has to equal 4 times 2 plus c. That has to be true for my velocity, because if I plug in 2 into my velocity equation, it has to be equal to 68. So that allows me to find out what c is. So 68 equals 8 plus c. So you subtract 8 from both sides. So that means c is 60. So now I know my real velocity equation that I started with was 4t plus 60. But I still need to find position. Well, just like we did with acceleration, we know for a fact that v of t is the derivative of position. So we're going to go backwards one more time. So when we go backwards again to find s of t, so what would I take the derivative of to get 4t? Well, that's 2t squared. Because when you take the derivative, you move the 2 out in front, so 2 times 2 is 4, subtract 1, you get t to the first power. And what do you take the derivative of to get 60? Well, that would be 60t. And again, there could be some c right there at the end. There could be a constant because there is a 0 here. And the only way you get a 0 at the end is if you have a constant. There might not be a c there at all. It might be 0 at the beginning. We don't know. But again, we're going to use this information here that they have given us to try to find that c for my position equation now. Because I know that if I plug in 2 for t into my position equation, again, it should be 138. So that's what I'm going to do. I'm going to say, okay, 2 times 2 squared plus 60 times 2 plus some c has to equal 138. So 2 squared is 4. 4 times 2 is 8. Plus 60 times 2, which is 120. Plus c equals 138. Then we get c by itself. So we subtract 8, we subtract 120. On this side, we're subtracting 128, which means c equals 10. So that means that my position equation is 2t squared plus 60t plus 10. So that's my actual position equation. Now we can finally answer that question that we wanted to answer in the first place. We wanted to find what is the distance traveled after 5 seconds. So what we need to do now is find s at 5. So plug in 5. So this is 2 times 25 plus 60 times 5 plus 10, which is 50 plus 300 plus 10, which is 360 meters. So basically what we just did here is we actually took or found the antiderivative. We went the other way. We said, okay, well, we know what the derivative is here. We know this is the derivative of velocity, so we went back to the original one by what's called taking the antiderivative. We worked it backwards. And the same thing, going from this to here, we had to work it backwards. So we're using our derivative rules, or what we've already known about the derivative, to actually work it backwards so that we can find our original equation in order to find our answer and plug in to find our distance traveled.